Okay, so what do we got here? Well, I've got three vectors, x1, x2, and x3. And we're told in the question, it's given to us that those three vectors form a basis for R3. So we don't have to prove that. That's not up to us to check. That's just given to us as an assumption. But what we are asked to do is apply the Gram-Schmidt process to come up with, well, in part A, first we want to get an orthogonal basis, and that's what the Gram-Schmidt will give you. And then a little adjustment at the end for part B, we can turn it into an orthonormal basis. So let's follow the Gram-Schmidt process exactly. So remember what the process says. You take your u1 to just be equal to x1. No adjustments, no projections, no subtractions. Just take whatever the first vector is, that's going to be your u1. Okay, so we've got one of our three vectors done already. But now the second one, u2, will start with x2, but that won't be the whole story. If we just end with x2 like that, then they won't be necessarily orthogonal, right? We want to subtract the component of x2 that's parallel to u1, the part that's already been accounted for with u1. And that will be our u2. So we're going to have to compute a projection here. So we better compute the projection of x2 onto u1. Okay, so there's a formula for that. We take the dot product of x2 with u1, and then we divide that by the dot product of u1 with u1. So that, and then that all gets multiplied onto u1. So that is the projection formula at work. But then, of course, there's a couple dot products that we got to compute. So let's do that now. So the dot product of x2, with the dot product of x2 with u1, well, you could, x2 is there, and what was u1? u1 was x1. I should finish this line off, 1, 1, and 1. So that's our u1. Okay, so the dot product of x1, or x2 and u1, we're going to have 1 times 1 plus 1 times 1 plus 0 times 1. That's what you get if you take the dot product of x2 with u1. Okay, and then, so what's that going to give you? That's going to give you 2. Okay, good. So that's x2 dot with u1. Now we've got to also take the dot product of u1 with u1. So, okay, well do that, and you're going to get u1, you're going to get 1, the first coordinate squared, plus 1, the second coordinate squared, plus the third coordinate squared. Really, what am I doing here? When you take the dot product of a vector with itself, that's the same as calculating its norm, except the only difference is you don't take the square root at the end. Oops, why did I have a 3 there? It should be a 2. Okay, so you're going to get 1 squared plus 1 squared plus 1 squared. That's what you're going to get when you take the dot product of u with itself. So that's 3. So that means this projection is 2/3 times u1. Okay, so that's what we want to subtract from x2 to get our u2 down here. So let's work this out. So x2 is 1, 1, 0. And then the projection, we're going to subtract 2/3 times u1, which is 1, 1, 1. Let's clean this up a little bit and get some common denominators. Let's write this as 3 over 3, 3 over 3, and then 0 over 3, minus, and then minus the vector, that's just 2/3, 2/3, 2/3. Okay, so what that'll give us, in the first coordinate, we'll have 1/3. Then in the second coordinate, we'll have 3 minus 2, which is 1/3 again. And then in the third coordinate, we'll have negative 2/3. Okay, and well, this brings me to a situation now that I actually mentioned in this remark. Remember what I said? At any point when you're working through the Gram-Schmidt, if you end up with a vector u and you don't really like the way it's going, because remember, we still have to find u3. And what's going to be involved with u3? We're going to start with x3, and then we're going to subtract the projection of x3 onto both u1 and then u2. So at some point, we're going to have to project x3 onto u2. And do you really want to take the projection onto a vector where it has a bunch of fractions floating around? If it's possible to avoid it, you typically will want to do that. So but there's limitations. You can't just change it to whatever you like. Otherwise you'll ruin the fact that your vectors are orthogonal. So what you do is you can scale it. You can stretch it or compress it. Like just change its length by multiplying by a non-zero scalar. And as long as you're multiplying by a non-zero scalar, you're going to end up with a vector that's parallel. And for the purpose of obtaining an orthogonal basis, that's good enough. So what we'll do, this vector isn't equal to the next vector, but they're similar in the sense that they're parallel. Okay, and you can see what I did. I just dropped the thirds on each coordinate. So just imagine if I multiplied the vector by 3, I'd end up with the vector 1, 1, negative 2. So the idea here, what I want to do, is I want to take this to be u2. So I'm going to take u2, instead of being 1/3, negative 2/3, I'm going to take it to be 1, 1, negative 2, just because that will simplify the rest of the calculations. I'd rather project onto this vector than project onto this vector. Okay, but they're technically not equal. So this is a modified version of the Gram-Schmidt now. Whenever you rescale a vector, it's modified, because so now you may not end up with the same result as your neighbor if they if they apply the Gram-Schmidt process verbatim and don't perform that scaling, then they'll end up working with this vector. And that's okay too. It's just going to be more difficult. And it doesn't really add any extra value to work with that vector. So okay, anyways, that's u2. We got our u2. Now we have to calculate u3. So how does u3 work? Well, you take u3 and you set it equal to, first and foremost, you set it equal to x3, but not totally equal to x3. We got to subtract some projections. We got to subtract the projection of x3 onto u1. And then also subtract the projection of x3 onto u2. And then that will end up, this will result in a vector that is orthogonal to both u1 and u2. Okay, so how are we going to do this? Well, let's start with this projection, the projection of x3 onto u1. Let's work that out right here. Projection of x3 onto u1. So based on the formula for projection, we have the dot product of x3 with u1 over the dot product of u1 with u1. And we've already actually worked out the dot product of u1 with itself. You end up getting 3. So that's one dot product that's already computed for us. But we will still have to compute the dot product of x3 with u1. Okay, well, x3 is this vector here, 1, 0, 0, and u1 is this vector here. So we're just going to get 1 times 1 plus 0 times 1 plus 0 times 1. And what's it going to work out to? You're going to end up getting 1. And then, yeah, the dot product of u1 in itself was just 3, so we already worked that out before. So we get 1/3 times, oops, I'm missing something here. When I wrote down the projection, this isn't the whole story. I just did the fraction where you get the scalar. That's the scalar portion, but we still had to multiply that on to the vector u1. So I beg your pardon. So that should be equal to 1/3 times u1. So what was u1? It was the vector 1, 1, 1. Okay, so that is our projection of x3 onto u1. But we also have to find the projection of x3 onto u2. So that will be following the formula. There'll be x3, the dot product of x3 with u2, divided by the dot product of u2 with itself. And that's all multiplied by the vector u2. Okay, so we got 2 new dot products to calculate. The dot product of x3 with u2. The end is in sight here, we're getting close. The dot product of x3 with u2. There we go. Okay, I had the wrong one circled because I still had them circled from the last one. I want to take the dot product of x3 with u2. So that's the dot product of these two vectors. So we've got 1 times 1 plus 0 times 1 plus 0 times negative 2, which works out to be just 1. Okay, so that's the dot product of x3 with x2, and then we're going to have to compute the dot product of u2 with itself. So the dot product of u2 with itself, u2 is over here, so we're going to end up with 1 squared plus 1 squared plus negative 2 squared, and that adds up to 6. Okay, so that means this projection is really just 1 over 6 times u2, which is 1, 1, and negative 2. Okay, so we've almost computed u3. So let's finally finish this off over here. So u3 is going to be given by x3 for starters, which was 1, 0, 0. That was x3 up here. And then we're going to subtract 1/3 times 1, 1, 1, because this was the projection of x3 onto u1. And then we're going to subtract now also 1/6 times 1, 1, negative 2. That was the projection of x3 onto u2. Okay, so what do you end up with? Well, let's worry about the first coordinate. The first coordinate will be 1 minus 1/3 minus 1/6, right? That'll be the first coordinate. Then the second coordinate will just have 0 minus 1/3 minus 1/6. And then for the third coordinate, we'll have 0 minus 1/3 plus 2/6, right? That's what you get if you multiply these two numbers. You get negative 2 over 6, but with this negative as well, then it becomes a positive, and you get positive 2 over 6. Okay, well, this actually can be cleaned up a bit more here. Let's write this, get everything as a common denominator. So if we have 6 over 6 minus 2 over 6 minus 1 over 6 for the first coordinate, then we'll have the second coordinate is negative 2 over 6 minus 1 over 6, and then our last coordinate, well, negative 1/3 plus 2/6, that's actually just negative 1/3 plus 2/3, so that's just going to be 0. Finally now, the first coordinate, 6 minus 2 minus 1 is 3, so you have 3 over 6, which is 1/2. So let's just write 1/2 for the first coordinate. Negative 2/6 minus 1/6, that's going to be negative 3/6, so that's negative 1/2, and then 0 for a second coordinate. Okay, so that is our u3. Again, if you want fractions, or if you want to remove the fractions, we can make the observation that this is parallel to the vector 1, negative 1, and 0. And then I could take this to be u3. So take u3 to be equal to 1, negative 1, 0. Okay, so now we've got ourselves an orthogonal basis. So B prime, that's the notation we'll use for our modified basis. So the first vector u1 was just 1, 1, 1. Right? That was our u1. Our second vector was u2, 1, 1, negative 2. So 1, 1, negative 2. And then our third vector was 1, negative 1, 0. So that is an orthogonal basis for R3. And that is the end of part A. So now that's the Gram-Schmidt process applied to turn a basis into an orthogonal basis. But now for part B, we want to turn this into an orthonormal basis. So, okay, remember this is U1. I'll write it here so I don't have to scroll up and down constantly. So this was U1, U2, U3. So for part B, remember what we do. Remember this question, what if we want an orthonormal basis? Well, then just normalize each of the vectors. So just take each of the vectors and replace it with 1 over its length times itself. So, okay. So what's 1 over, well, let's actually find the norm of each of these vectors first. The norm of U1, that's the square root of 1 squared plus 1 squared plus 1 squared, which is equal to the square root of 3. Okay, and the norm of U2 squared, the norm of U2 is going to be the square root of 1 squared plus 1 squared plus negative 2 squared. Okay, and that works out to being 1 plus 1 plus 4 inside the square root, so you get root 6. And then finally, the norm of u3, well, just square each of the coordinates and add them up, so we get 1 squared plus negative 1 squared plus 0 squared, and you end up with root 2. So now that we have the norm of each vector, we can make a new basis. So I'll call this one B double prime now, because we're modifying the basis a second time. So here's what the vectors are. We'll take 1 over u1, 1 over the norm of u1 times u1. So that'll be the first vector. The second vector will be 1 over the norm of u2, which is 1 over root 6, multiplied by u2, which is 1, 1, negative 2. And then the last one will take u3, but we'll multiply it by 1 over the norm of u3, which is 1 over 2 times 1, negative 1, and 0. Okay, so that is now an orthonormal basis. And you can see that the last few steps that we did to turn it into an orthonormal basis, that's really nothing, that's not anything genius, right? We've known for a long time we can take a vector and resize it so it has length 1. That's not particularly inventive. It's the Gram-Schmidt process is the first part, the part that comes up with the U1, the U2, and then eventually the U3. This is really the Gram-Schmidt process. The part at the end where we just rescaled them so that they would be so that each vector would have length 1. That's not really any part of a special process, but nonetheless, you can call it the modified Gram-Schmidt process to give you an orthonormal basis. So to finish this off, this is an orthonormal basis for R3. Okay, so that's the Gram-Schmidt process. If you have a basis for a subspace and you don't really care if the vectors are orthogonal, or you don't care how long the vectors are, then this method is not for you. But if you want to be working with a basis that's orthogonal, then this is. So that's what it's for, and that's how it works.